Colligative properties are properties that depend upon only the concentration of solute particles and not upon their identity. And when we talk about solute particles, we're talking about all particles in solution. So if we dissolve an ionic compound in solution, we are talking about the concentrations of the ions in solutions. These colligative properties include vapor pressure of solutions, boiling point elevation, freezing point depression, and osmotic pressure and osmotic flow of solutions. So concentration of ions, when we dissolve ionic compounds into solution, we'll need to know the ionic concentration for these colligative properties. So we're going to represent that with IM. Capital M is molarity, and I is the Van't Hoff factor, as the number of ions in the compound. So we're going to generally assume complete ionization of ionic compounds. So sodium sulfate is going to form 2 sodium ions and 1 sulfate ion, for a total of 3 ions in solution. So our concentration of ions will be IM, so 3, Van't Hoff factor of 3 times the 0.5 molarity will give us 1.5 for the concentration of ions in solution. So Van't Hoff factor is going to be the number of ions in a compound over the compound. Or, if we're calculating a Van't Hoff factor from measured concentrations, it will be moles of solute in solution, moles of ions in solution, divided by the moles of solute dissolved. We're going to generally assume that we have 100% ionization. So that means that we can just estimate our Van't Hoff factor by the number of ions in the compound. This isn't always true, and from experimental work we can determine the actual Van't Hoff factor. The actual Van't Hoff factor will be smaller than our initial estimate of complete ionization. So some Van't Hoff factors for non-electrolytes. Non-electrolytes means it's not an ionic compound, and it will not dissociate in solution. So we have a Van't Hoff factor of 1. That's our expected, that is our actual. For table salt, we're going to expect 2 ions, sodium ion, chloride ion. We're going to get slightly less than that. That means there's some ion pairing going on. So we don't necessarily have complete dissociation. We might have some unionized NaCl in solution. We might have some Na2Cl with a positive charge. We might have some NaCl2 with a negative charge. So we might have a small amount of some paired ions in solution. For magnesium sulfate, we would expect 2. 1 magnesium, 1 sulfate. We're getting to 1.3. We have a larger amount of ion pairing going on. For magnesium chloride, we'd expect 3 magnesium plus 2 chlorides. We get 2.7. For potassium sulfate, we would expect 3. We get 2.6. For ferric chloride, we would expect 4, and we get 3.4. So we can have the expected measure to be equal to the expected, but we won't have a larger number. Now we know that solvents have a vapor pressure to them. They evaporate away. Most of them do. Not all of them. But most of them do. They evaporate away on us. So because they can evaporate away, they have a vapor presence that creates a vapor pressure. So if we have a liquid in a closed container. We'll pump. No, we don't have to take air out. We just close the liquid up in a sealed container. There might be some gas up there. It'll start off at atmospheric pressure. But then as we let the container set, if we're measuring the pressure, we'll see that the pressure increases. But then at some point the pressure stops increasing. The increase in the pressure of the container is the partial pressure of the liquid evaporating. If we have an open container, the liquid evaporates away. So the liquid evaporates to the airspace above it, but then the air is taken away, so the new air has none of the liquid in it. So it keeps putting more into that airspace. So the evaporation process continues until the partial pressure of the liquid equals a certain amount. That amount that we get in that closed container. It does change with temperature. So as we increase the temperature of the container with the liquid, increase the temperature of the liquid, you'll notice the pressure increase. So the vapor pressure of the liquid is increasing. So a liquid wants to get a certain pressure above it at a specific temperature. So it's temperature dependent. If the pressure above it is less than that specific amount, it's going to evaporate until it reaches that pressure above it, that partial pressure. For solutions, as we dissolve something in that liquid, the solvent, that liquid, as we dissolve something in it, well, we're going to look at non-volatile things that we're going to dissolve. So we're going to dissolve solids into it. So as we dissolve a solid into a liquid, that is a non-volatile solute into a volatile liquid, solvent, the solute will be on the surface of the liquid to some fraction. And the solute on the surface of the liquid will not let evaporation occur at its location, since it cannot vaporize. So the pressure of the liquid over the liquid decreases. There's a lower exchange between the liquid and the gas. So as we increase the fraction in terms of particles, so mole fraction of the solute, the vapor pressure of the solvent decreases. So this is the relationship. So the mole fraction as the mole fraction of the solute increases, that means that the mole fraction of the solvent decreases. So the vapor pressure decreases as the mole fraction of the solvent decreases. And it turns out to be a linear relationship. So this equation can describe that relationship. So P0 is the vapor pressure of the pure liquid, pure solvent. we found that as the fraction of the solvent in the solution decreases, the vapor pressure of the solvent decreases over the solution. So it's a pure linear relationship of pressure times mole fraction will give us the partial pressure of the liquid over the solution. This is called Raoult's law, and this is for a non-volatile solute. So this is when we have a solid, ionic or covalent, dissolving into a liquid. If we are doing a ionic solid, we will have to do the mole fraction of the ions as part of the total solution. This relationship, we call this to be an ideal relationship. There's no corrective fudge factors in the relationship. So this occurs under certain combinations of solvent and solute, but not for all. So for all, they do not follow this relationship. They exceed or don't reach the value that described by this relationship. For non-ideal combinations of solvent and solute, Raoult's law works, or is a good approximation for dilute solutions. So that is when the mole fraction of the solvent is greater than 95% or greater than 0.95 mole fraction.